1.6 basic properties of Markov chains. We start with a transition matrix, and it's denoted with the letter P, but a transition matrix is a matrix that represents the probability of changing from one of a set number of states to another, including staying the same. So we are dealing with probabilities. So think about what that means. First of all, our transition matrix is going to be square. You're going to see 2 by 2 or 3 by 3 most often, but it could be bigger than that, 4 by 4, 5 by 5. It's going to be square. All entries are between 0 and 1. This is because we're talking about probabilities. They are all probabilities, so you're going to be looking at probability numbers between 0 and 1. The sum of entries in each row is 1. And the reason for that is because each row indicates like everything that would be possible. Everything that would be possible would add up to 100% or a probability of 1. Example 1, find each probability depicted in the transition matrix, then draw a transition diagram. So this is a very important question. You have to be able to read the matrix. So the matrix is going to look like this, basically. A lot of the times you're not going to see all those extra words, but this is trying to show you the probability of transitioning from one thing to a different one. Okay, so we are talking about matrices. You always want to start with the row and go to the column. Rows before co's still. All right, so I've got kind of my own little notation that I made up here. P is that transition matrix or probability, but we're finding the probability of going from middle to upper. All right, probability of going from middle to upper. From middle to upper would start here and end here. We're looking at this entry, 0.18. Doesn't have to be hard. That's all we're doing. So then the next one says the probability of going from lower to middle. From lower to middle is this entry right here. We're going from lower to middle, 0.28. So what do you think probability of upper to lower is? 0.12. All right, simple as that. From upper to lower, that's what we're looking at. Now we're going to draw a transition diagram. Okay, then draw a transition diagram. So a transition diagram is a picture of this matrix. So what you'll want to do is you want to have like I'll say L, M, and U. Those are my 3 states. So what I'll do is I'll make like a circle with an L in it, and a circle with an M in it, and a circle with a U in it. Those are just representative of lower, middle, and upper. So what we do is we're going to have, see how there are 9 numbers in the matrix? We're going to have 9 arrows in our drawing. And if I'm doing, let's do lower first, all right? Lower to lower, so lower back to itself is a 0.65 probability. Lower to middle is a 0.28 probability. And lower to upper is 0.07. Now, those numbers should add up to 1. That was part of the definition above, but that's my lower to each of the other 3 states. Now let's look at middle. So let's look at middle. If we go from middle to lower, that's 0.15. And middle to middle, or back to itself, is 0.67. And middle to upper is 0.18. Now I'm going to do upper. Upper to lower is 0.12. Upper to middle is 0.36. And upper to upper, or back to itself, is 0.52. 9 numbers in the matrix, 9 arrows in the transition diagram. They both represent the exact same information. All right, and so now we have the definition of a Markov chain. A sequence of trials of an experiment is a Markov chain if, number one, the outcome of each experiment is one of a set of discrete states. 2, the outcome of an experiment depends only on the present state. And 3, the transition probabilities remain constant from one transition to the next. Let's look at example 2a. A small town has 2 dry cleaners, Johnson and North Clean. Johnson's manager hopes to increase their market share by advertising. After the ad campaign, it was found that there is a probability of 0.8 that a Johnson customer will bring their next batch of clothes to Johnson. Further, it was found that there's a probability of 0.35 that a North Clean customer will switch to Johnson for their next batch. Give a transition matrix and a transition diagram. Well, I prefer a matrix. I think it's a little bit easier to do a matrix, but you have to know how to set it up, I suppose. Notice there are 2 different states. Either you can be a Johnson or North Clean. So that tells me that it's going to be a 2 by 2. So the way I would set up this matrix is I would say there's Johnson and there's North Clean. So I would set up a 2 by 2 where there's Johnson and there's North Clean. So when you look at the numbers, it was found there's a probability of 0.8 that a Johnson customer will bring their next batch to Johnson. So from Johnson to Johnson is 0.8. That number goes right there. From Johnson to Johnson is 0.8. The only other number in this problem says there's 0.3 probability, 0.35 that North Clean will switch to Johnson. So what that means is from North Clean to Johnson is 0.35. Now it's a little bit tricky here because there are 2 other numbers. They aren't given to you, but it's really pretty easy to figure them out because earlier we learned that the rows have to add up to 1, right? So if the row has to add up to 1, then that means this number over here, Johnson to North Clean, must be 0.2. They didn't tell me that, but I can figure that out. And then you look at the second row. If those numbers in that second row have to add up to 1, then this number must be 0.65. That is your transition matrix. Now we're going to make a transition diagram. Well, there are only 2 states in this problem. There's Johnson and there's North Clean. So we're just drawing a picture of those 4 numbers. So if I look at Johnson first, from Johnson back to Johnson is 0.8. And from Johnson to North Clean is 0.2. From North Clean to Johnson is 0.35. And from North Clean back to itself is 0.65. There's your transition diagram. Example 2b, North Clean had 128 customers drop off a batch of clothes this week. Use a tree diagram to show how many of those customers North Clean can expect will return for their second and third batches of clothes. All right, so now we're trying to make a prediction, okay? And that's what Markov chains are good for. They're good for predicting things. So let's see, North Clean had 128 customers. So what we're going to do is we're going to start at North Clean. That's what it says. We're going to start at North Clean and 128 customers. So if you think about what can happen for their second batch of clothes, well, either they go back to North Clean or they go to Johnson, one or the other. So a tree diagram, you've really only got 2 possibilities. Either they will go to Johnson next time or they will go to North Clean next time. And those probabilities, according to the transition matrix, from North Clean to Johnson was 0.35, and from North Clean back to North Clean was 0.65. That's straight from the transition matrix above. So if you think about it, 128 times 0.35, or 35%, 35% of 128, let's call that 45. This means 45 people are at Johnson. All right, and 128 times 0.65, 84, 83, 83, 83. 83 plus 45 equals 128. But after, on the second batch, we can see, well, look at the question. How many of those customers can North Clean expect will return for their second batch? Well, second batch is 83, right? 83 right here. But now we need the third batch. So if we're at this Johnson right here, you've got two choices. Either you go to Johnson for your third, or you go to North Clean for your third. Okay? And Johnson to Johnson was 0.8, and Johnson to North Clean was 0.2. That's straight from the transition matrix above. But if you were down here at North Clean for your second batch, you have these two options. Either you go to Johnson for your third, or you go to North Clean for your third. And again, North Clean to Johnson was 0.35, and North Clean to North Clean was 0.65. So I can figure out this number. There were 45. There were 45 here. 45 people brought their second batch to Johnson. So, for this number, I could do 45 times 0.8. And for this number, I could do 45 times 0.2. Well, I really only care about North Clean. So 45 times 0.2 is 9 right here. I mean, this is 36 and this is 9. 83 people were at North Clean for their second batch. And so this number is going to be 83 times 0.35 is 29. And this number down here is going to be 83 times 0.65 is 54. So we want to know how many are going to return to North Clean. And so that's this number and this number. Okay, so if we're talking about how many of those 128 people returned to North Clean for their second batch, 83. But for the third batch, we're looking at 9 plus 54. 9 plus 54 is 63. 63 people return for their third batch. That's a tricky question with the tree diagram. Once we figure out how these matrices and stuff work, we won't want to use a tree diagram. We'll just use matrix multiplication. This slide is important. A transition matrix P shows the probability of change from one generation to the next. To examine changes over more than one generation, we're going to use powers of the matrix. And this is where you're going to want a calculator. We're going to take that matrix to the second power, third power, fifth power, ninth power, whatever. All right. So we're talking about generations. So for example, if you went from a mother to a child, that's one transition. That's one transition from mother to child. But if I went from mother to grandchild, think about the number of trips to the hospital or whatever. Okay, from mother to grandchild is 2 transitions, and from mother to great grandchild is 3 transitions. Seems easy, but it gets kind of confusing at times how many transitions there are. Example 3 says P is the transition matrix from the example about income classes, lower, middle, and upper. All right, so you should recognize that. Example A says find P squared. I want P squared, and we could do it by hand if we took that matrix and multiplied it times itself, but I don't want to do that. So let's do a matrix calculator. So you can do it on your own. I like the Desmos one. I think it's pretty good. So I'm going to do a new matrix. This is a 3 by 3. And it was 0.65, 0.28, 0.07, 0.15. Let me know if I type something in wrong. 0.67, 0.18, 0.12, 0.36, 0.52. So that's my matrix. Notice on the paper it's called matrix P, but inside this website it's called matrix A, whatever, doesn't really matter what we call it. But we've got that 3 by 3 matrix and we want to square it, right? So we're going to take this matrix and then to the second power. And notice you get those messy looking decimals or whatever, and that's fine. If you look at fractions, not any better. If you've got ugly looking fractions, I'd much rather see decimals. All right, don't give me ugly fractions, give me ugly decimals. I'd prefer that any day of the week. But that is our P squared, I guess. All right, that is our P squared. We want to copy that over. Whoops, not that. So we have 0.4729, 0.3948, 0.1323, So that's our squared matrix. And that's going to tell us the transitions over 2 generations. So part B says, find the probability that a middle class person has an upper class grandchild. So we're going from a person to a grandchild. So if we're going from a mother to a grandchild, that was 2 transitions, right? We're doing 2 transitions. And so how I would write this is like this. We're going the probability from a middle to an upper, but in 2 transitions. That's how I write it. And so remember what the matrix represents. We've got lower, middle, and upper, lower, middle, and upper. So if I want from middle to upper in 2 transitions, I look at the square matrix. From middle to upper is this number right here, 0.2247. Part C says, find the probability that an upper class person has a lower class grandchild. So again, grandchild implies that there are 2 transitions, but we're going from upper to lower in 2 transitions. From upper to lower in 2 transitions is 1944. 0.1944. The hard part is getting the square matrix. If you had to do that by hand, it would be kind of ridiculous. But with a calculator, that's not going to be that hard. Make sure you know how to use it. So example 4, we're talking about the same exact transition matrix, but this time they want P3. They want P to the 3rd power. The 3rd power is going to talk about, transitions to great-grandchild. So 3 transitions. So we go back to that matrix calculator, and since we already have it typed in, we would just do a, and then this a to the n should let me type in an exponent, a to the n, and we want it to be to the third power. Okay, so again, we've got some ugly looking decimals. I'd rather those decimals than those fractions, though. Don't give me those fractions. Give me the decimals. Okay, give me the decimals, and we'll copy that over. So we've got is that right? Yeah. Okay, that's P3. Again, you've got numbers between 0 and 1. The rows should all add up to 1. Okay, that's great. Don't forget what we're talking about. We're talking about transitioning from lower, middle, upper to lower, middle, upper in 3 transitions now. This is the matrix that would tell us 3 transitions. The original only told us 1 transition from parent to child, but this one tells us from parent to great-grandchild. And part B says, find the probability that an upper class person has a middle class great-grandchild. So great-grandchild is the one that tells me that it's P3. But we're going from upper to middle in 3 transitions. And that's this number right here, upper to middle in 3 transitions. So 0.487668. Part C says find the probability a lower class person has a lower class great-grandchild. So again, you got to pay attention to this so you know which matrix to look at. Great-grandchild is 3 transitions. We're going probability of lower to lower in 3 transitions. Well, lower to lower is right there. 382,481. 0.382481. And what that means is there's about a 38% chance. So you think about it this way, okay? You know, if you're a lower class individual and you have a kid and they have a kid and they have a kid, okay, there's a 38% chance that your great-grandchild would also be a lower class individual. That's what that's saying, okay, according to these numbers. Now, for whatever reason, students really struggle with this part. So I want you to really, really up the focus. A probability vector is a row matrix, and we've talked about that in the past, that shows the distribution of the total population among its states. Since they are probabilities, each entry is between 0 and 1, and the sum of all entries is 1. The initial distribution is the first probability vector. So it's usually marked like x0 or x0. Okay. So what that is talking more about the breakdown than the probability. So, you know, if I counted the number of boys and the number of girls or in this classroom, okay, maybe 60% are girls and 40% are boys. So that vector would be 0.6, 0.4. Okay, that's just the breakdown. And then, you know, something happens next year, I've got 0.65, 0.35. I've got the different breakdown. It's not necessarily talking about the probability of changing from one to another. It's just talking about where we are. What is the population? All right. So Number 5 says the probability vectors below represent the percentage of the U.S. population that subscribe to a paid video service such as Netflix, Hulu, etc. in the years 2017 through 2020. The number on the left represents subscribers, and the number on the right represents non-subscribers. Give the initial distribution. Well, initial distribution, that's x0. That's the first one. So literally all I want you to do is write it down. You've got 0.469 and 0.531. Now remember, they said it's between 2017 and 2020. So we're talking 2017, 2018, 2019. Whoops. Nope. And 2020, like that. And so that initial distribution is talking about where we were in 2017. That's saying 46.9% of the population subscribed and 53.1 did not subscribe. That's what it's saying. It's not talking about the probability of going from one to the next. That's something else. That's just telling what the population is, what the population does. So part B says, what percentage of the population subscribed in 2019? Well, they're talking about this number right there. That's the percentage, okay? That's the percentage that subscribed. So you can call it 0.547, or you can say 54.7%. Since they asked for the percentage, you could call it a percentage right there. Part C, what percentage of the population did not subscribe in 2018? So that's this number right here, 48.3. Or I'd be fine if you gave me 0.483. Describe the trend. Well, paid subscribers are increasing. That's what it looks like. You know, you look, it started here, it goes here, it goes here, it goes here. Looks like the subscribers are increasing to me. Okay. Distribution vector. Okay, so again, we're talking about vectors, and this is the part that people really struggle with. The distribution vector x sub n for any number of transitions is this. X sub n equals x sub 0, that's the initial, times p to the nth power. Now notice the difference between subscript and superscript. The superscript is an exponent. So this last n right here at the end, that's an exponent, but the other two are just telling you which one we're looking at. Okay, the subscript is just saying it's the 0, it's the first one, or it's the nth one. So example 6, recall the income class example from earlier with the transition matrix over there, P. X0 is the initial distribution of incomes. And so that's kind of where we start. What that means is 21% of the population was lower, and 68 was middle, and 11 was upper. All right, that's the percent of the population, not necessarily probability. That's just talking about how many were this, and how many were this, and how many were this, or the breakdown. Find the distribution after 2 generations. Students really struggle with this, but you just have to use this formula. Okay, we have to use that formula. So we want to find after 2 generations, we want to find x2. And this isn't very hard, especially with a calculator. In order to follow that equation, it says we have to take x0 times p to the nth power, and n is 2 in this example. So we want to find x0 times p squared. Okay, now remember, x0 is this. So I'm going to do that on my calculator. I've already got matrix A in there. All right, matrix A is right there. We've got it. But we want that x0. So we need a new matrix, and it's got 1 row and 3 columns. and it was what? 0.21 and 0.68 and 0.52. No, not 0.52. 0.11. Those numbers have to add up to 1. 0.52 would have been too big. Okay, so check it out. Now I've got my transition matrix and I've got my initial vector. Okay, so notice all the formula says to do is multiply them, but I want you to notice something because I'm going to mess up on purpose. Okay, if I try to multiply them, I get an error message over here. Why? What? P to the second? Okay, it should be B times A, not A times B. Does it matter? Remember, you have to look at the dimensions, right? And an A was 3 by 3, but B is a 1 by 3. You can't multiply that. That's not going to work. Okay, good answer. So I don't want AB. I want BA. Okay, wait a minute. That's not right either. It's got to be squared, right? Because I want the second generation. Okay, I want B times A squared. I want the initial times the transition squared, and I get that. Okay, I get that, which is a new distribution. So I'm going to copy that over. Okay, so let me just kind of write what I did here. We took the initial, which was 0.21, 0.68, 0.11, and we're multiplying it by 0.65, 0.28, 0.07, 0.15, 0.67, 0.18, 0.12, 0.36, and that's a 5, by the way. And 0.52 squared. Okay, so if we multiply the initial distribution times the square of the transition, we got something really gross. Find the distribution after 2 generations. And what that means is, after 2 generations, 27% is lower, and 51% is middle, and 22% is upper. That's what that means. That's the new breakdown. Those are not probabilities. That's the new breakdown. Okay? Now I want to find the distribution after 5 generations. And so all I have to do is use this formula. If I want to find x5, then I need to take the initial times the transition to the 5th power. And if I've got a calculator, it's easy. I take that initial times the transition to the 5th power. My initial was B, and my transition was A. I need to go to the 5th power, and there it is. Okay, almost done. Let me finish up. I don't know if I'm going to have room, though. It was 0.284. Let's just round off here. 0.4899 and 0.2257. Normally, I wouldn't want to round off. But since I'm out of room, there we go. That is the distribution. You might have to answer a question like, what percentage of the population was upper class after 5 generations? And then you'd say something like 22.5, 22.6.